Hello all the crazy people out there, my name is Michael, I like wizards and dragons and making games, and welcome back to 3D Games in GameMaker. This is a bit of a big topic. Today we are talking about normal mapping. Normal mapping is one of the more popular 3D lighting techniques out there. If you're not familiar with how it works, normal mapping is a way to, shall we say, fake detail on 3D geometry and make it look like there's more geometric detail than there is by modifying the way that the lighting normal calculations are handled. The simplest kind of 3D lighting in computer graphics is flat shading, where each triangle has its own surface normal, and the lighting calculations are done with the surface normal for every triangle. An evolution on that would be smooth shading, where the normals are defined separately for each vertex and smoothed over the entirety of each triangle. And normal mapping is essentially a step beyond that. So instead of defining the surface normal for 3 points on a triangle and interpolating across the triangle, we're going to instead define a surface normal for each fragment, for each texel on the texture map that we're using to render. And this allows each fragment that you draw to have its own normal, as it's sampled from the normal map. And when combined with existing lighting information, so directional lights, point lights, etc., you can use this per pixel surface normal information to make it look like a simple piece of geometry has a lot more geometric detail than it actually does. So in my example here, I have the Master Sword from The Legend of Zelda Breath of the Wild. These things come with a base texture image. In standard rendering, that's known as the diffuse texture image. In physically based rendering, that's going to be known as the albedo, and also a normal map. And those will be my test subjects for today. So before we get into writing any code, let me just show you what this normal mapping project looks like. I've cut out pretty much everything from previous tutorial videos that isn't essential to what we're going to be doing today because I don't want the clutter to get in the way. I have 3 vertex buffers that I'm going to be loading into the game with just buffer load and converting those to vertex buffers. Those are going to be the sword, the sword's sheath, and the ground. I got rid of all the other stuff. And I have a couple of texture maps to go with this. So this is the ground, just a series of plain, boring old bricks that go on the ground. This is the normal map for the ground, and if you've ever seen a normal map before, you're probably very familiar with this light blue, light purplish color sheen, and I'll get to why they are often colored to that in due time. We've also got the texture map for the sword's sheath, the normal map for the sword's sheath, and the texture map for the sword itself, as well as the normal map for the sword itself. Again, light blue, light purple in color, there's a little bit of light green and light red. All 6 of these images are on their own texture pages, as is often how you want to set things up when you're doing 3D in GameMaker. And in the draw event over here, I'm not really doing anything exciting. I'm setting the basic 3D stuff shader. I'm drawing all of the vertex buffers. The swords are going to have a little bit of rotation applied to them so that we can see them rotating on the spot. Alright, so first some prerequisites. You're not going to need to know any really complicated advanced linear algebra to make this work, to make normal mapping work, but you are going to want to know some basic 3D rendering, obviously. You're going to want to know how lighting calculations work. You're going to want to know what N.L means and the whole works. You're also going to want to know how to set up multiple texture samplers. Again, this should be fairly obvious because we're going to be feeding a normal map sampler into the fragment shader to make this work. And if you know what different coordinate spaces mean, like view space, object space, world space, and if you roughly know how to multiply a value by a matrix to convert between different coordinate spaces, that's going to make your life a lot easier. You're also going to want to know about encoding normal vectors as colors, because the normal vectors are encoded in the normal maps as colors, and we're going to need to be able to get it back, and also we're going to need to be able to do some additional things that GameMaker makes us do. I have made videos on all these things in the past. If you want to go get caught up on them, click on the card popping out of the corner of the screen, or I will also have links down in the description of the video. So the red, green, and blue channels on these normal maps are all encoding a normal vector inside a color. The color channels, as you probably know, range from 0 to 1, and since the components on a normal vector can range from -1 to +1, we have to do a little bit of conversion if we want to be able to get an actual useful normal vector out of the texture map. This is a pretty simple arithmetic operation. You just have to multiply the sampled value by 2 and subtract 1. And just like that, you have the normal vector for the surface that you're rendering. However, this isn't immediately useful to us, because the normal vector that you get off of the normal map is going to be in what is known as tangent space. So the same way that we have object space, view space, and so on, Normal maps encode the surface normal in tangent space. And I think the easiest way to imagine tangent space is to imagine putting the camera on the surface that you're currently rendering, like at the location of the textile that you're currently in the middle of processing. And the view matrix of the camera, if you were to put the camera at the exact location of the fragment that you're currently drawing, that matrix would represent the fragment's coordinate in tangent space. Now, for this operation, we don't actually care about the fragment's position in space, we just care about its orientation. And so the tangent space matrix can just be a 3x3 matrix instead of a 4x4 matrix like you would usually see in a view matrix. It boils down to the upper left 3x3 of the view matrix, since that is the part of a 4x4 matrix which represents orientation. But that aside, a view matrix is composed of a forward, an up, and a sideways vector, and we can construct a similar matrix composed of a similar set of vectors if we want to represent a fragment's orientation in tangent space. So our forward vector in this analogy would be just the regular surface normal that we're used to dealing with. This is the vector that points straight out from the surface that we're rendering. The camera's sideways vector is going to be something new, which I haven't talked about before in one of these YouTube videos, and that is going to be the tangent vector. The tangent vector, as the name implies, is a vector which is tangent to the surface that lies flat on the surface. And lastly, the camera's up vector would be what is somewhat anticlimactically known as the bitangent vector. This is also going to be a tangent vector, but it's going to be orthogonal to, it's going to be at right angles to both the normal and the original tangent vector. And of course, all three of these vectors have magnitudes of 1. They're all orthogonal to each other. And taken all together, they form 3 axes in 3D space, which represent the orientation of the fragment that we're dealing with. And we can put them all together in a 3x3 matrix to convert vectors into and out of tangent space. And now that we have a matrix which represents the surface normal, tangent, and bitangent of a surface in space, we can take the value that we sampled from the normal map, we can multiply it by the, let's just call it a TBN matrix, because I'm not going to say that many syllables every time I refer to this. And that will convert our normal map value into, in my case in this video, into world space so that we can actually make use of it in 3D lighting calculations. So, calculating the tangent vector is kind of a whole thing. I've made a video in the past about calculating normal vectors, and that's pretty straightforward. In a nutshell, you just take the edge vectors of whatever triangle you're trying to calculate the normal of, you find the cross product of those two edge vectors, and then you normalize that so that it has a magnitude of 1. And if you want smooth normals, you can just do that, but do it for every triangle in the mesh and then just average them. Calculating tangent vectors are a little bit more involved. I do want to make a video on that at some point in the future, but for right now, in this example, I'm actually just going to load them in from a vertex buffer. I've pre-computed them ahead of time. If you want to know how to do this yourself, I'll put a link to an article about it down in the video description. Otherwise, again, I will make a video on it one of these days. And like I said, once you have the normal and tangent vectors, you can just use the cross product of those two to generate the bitangent. Strictly speaking, you only need a normal and tangent vector for that reason, and you can pretty easily compute the third in the shader. But for the sake of simplicity, I've gone and computed all 3 ahead of time and stored them in these vertex buffers. So since we have added additional data to each vertex, besides the usual position, normals, texture coordinate, and color, this means that if you were to just load in one of those vertex buffers from a file and then try to draw it with the regular 36-byte vertex format that we're used to, you're going to be getting all kinds of silly nonsense like this. If you've ever seen something like this happen, this is what happens when the vertex format of what you try to draw doesn't match the vertex format of the data. I like to call this little effect "help my GPU is on fire," because sometimes if your GPU is dying, you will see things like this. So if you want to be able to see anything that looks remotely like the master sort, I'm going to have to go and edit the vertex format. And you might want to simply say vertex format add normal 3 times, because that makes sense. We're dealing with 3 different normal vectors. We're dealing with the normal vector itself, the tangent, and the bitangent. But now we have to talk about the fact that GameMaker is still using a shader language from about, I want to say, like 12 years ago now.
Hey.
Or at least that's the version of OpenGLES that we're using. So, unfortunately, there are some limitations on what we can create as vertex attributes, and you cannot create additional normal attributes, which makes me really sad. you can only add additional texture, coordinate, and color attributes. So because cramming a whole entire normal vector into a texture coordinate is going to be a little bit, let's say, not straightforward, we can instead use colors. So I did mention that encoding normals as a color and by extension decoding normals as colors is something that we're going to want to know about in this video, and that is not only going to be so that we can sample from the normal map and get a vector in the proper range from the normal map, but also because the tangent and bitangent vectors are going to be encoded as colors. So we're going to be using the red, green, and blue channels of additional color attributes. Alpha we're just going to be ignoring, and then we're going to have to convert those back into the range of -1 to +1 in the shader. Hey. So now if I run the game, if I don't do anything else, but if I run the game, we're at least going to see something. Okay, so we've got no normal mapping happening. We've just got a diffuse texture information and a little bit of a basic N.L lighting. I believe this is flat shading. I believe this is per triangle. The basic 3D stuff shader is pretty much the same as it was in most of the other videos that I've made on 3D lighting. So there is a basic directional light. I'm not even passing that in as a uniform. I'm just hard coding it. A basic directional light, and then we're doing the N.L thing and using that to compute diffuse lighting. But for normal mapping, I'm going to need to make some edits to both the vertex shader and the fragment shader. So let's start with the vertex shader. So I did mention adding additional attributes as colors, and I believe this is actually not a GameMaker thing. I believe this is actually like an OpenGL shader language version, like 1.0 thing. Hey. So we've had a few videos over the years which have become a little bit out of date as GameMaker updates and adds new features, and between you and me, I'm kind of hoping that this is one of those videos. I hope this joins that list sooner rather than later, because this is kind of annoying when you want to make additional vertex attributes work in a shader in GameMaker. It's a whole thing, but like I said, generally the only additional attributes that you can add to a shader in GameMaker are additional color attributes or additional texture coordinate attributes, and they have to be named in a particular way. So in color, with or without a U, in color 0, 1, 2, 3, or 4, or so on, are going to be the subsequent ones. Yes, it's annoying. Yes, it's weird. Yes, it definitely trips up people who are trying to do things with vertex attributes who aren't aware of this particular nuance. But for now, we're just going to have to live with it. Anyway, complaining aside, I am going to create the 3x3 TBN matrix here in the vertex shader, and I'm going to pass it to the fragment shader as a varying. So instead of passing just the vector 3 surface normal to the fragment shader as a varying, I'm going to instead make this a 3x3 matrix, and instead of just being the world space normal, I'm going to say the TBN. So that's going to be the TBN matrix. And that's going to be sent over to the fragment shader, so let's say varying mat3v underscore TBN over here in the fragment shader, and we'll get to using that when the time comes. So firstly, I'm going to need to take the input normal that we're getting just from the regular normal attribute, convert this into world space as we're doing here, as we've done before. I'm going to say vec3 world space normal is going to equal this. So you take the normal, give it a homogeneous coordinate of 0, multiply it by the world matrix, and just look at the XYZ. We're going to do something similar for var vec3, let's say world space tangent. We're also going to take the world matrix, multiply that by, instead of the input normal with a homogeneous coordinate of 0, I'm going to say input color, and since this is a normal vector encoded as a color, like I mentioned earlier, we're going to need to take the red, green, blue out of this. We're going to need to multiply it by 2.0, and rather than adding 1, subtract 1, and that is going to give us the vector with components in the range of -1 to +1, and then of course homogeneous coordinate of 0. Let's normalize this again, and take the XYZ, like that. Yeah. And the same thing for the bitangent. And the bitangent is, of course, going to be, small mistake, input color 1.rgb is the tangent vector, and the bitangent is going to be input color 2. Same thing. So now we have 3 vectors, 1 surface normal, 1 tangent, which is pointing tangent to the surface, and 1 bitangent, which is perpendicular to both of those, creating a 3-dimensional coordinate system. Anyway, we have these 3 vectors, and I'm going to, did it again, v underscore tbn. I'm going to assign a value to this. This can simply be a matrix 3, which is going to be composed of either 9 values or 3 vector 3s. Those 3 vector 3s are going to be world space tangent, world space bitangent, and world space normal, like I said. Now this, I'm fairly sure, is a GameMaker thing, because GameMaker sometimes does things to 3D cameras when you use its built-in camera system. You're going to want to negate the tangent and bitangent vectors in this TBN matrix over here. You're just going to want to toss a negative sign in front of them. I don't believe you need to do this in general computer graphics, but in the same way that GameMaker does things to our 3D cameras, that sometimes means that we have to do things like use a negative field of view for our 3D camera. We're going to want to throw a negative sign in front of that tangent and bitangent vector. So I believe that's it for the vertex shader. I am everything else I'm passing the texture coordinate along as a UV. Not dealing with vertex color right now because that's just not very important and I don't want it to get in the way. So let's head on over to the fragment shader. So aside from setting up the TBN matrix varying input from the vertex shader, we are going to want to also make sure that we can recognize a texture sampler for the normal map. I'm going to say uniform sampler 2D. Let's call it sampler underscore normal. And this is a sampler that we're going to want to supply to the shader whenever we draw a vertex buffer over here. So if you run the game now, nothing's going to happen. We currently, yeah, that won't even compile. We're trying to make use of a normal vector for the m.l calculation, which we currently do not have because all we have is the TBN matrix. So we're going to need to use this. We're going to need to get the sample the value from the normal map, and we're going to need to multiply that by the TBN matrix if we want to be able to get the fragment's orientation in world space. Let's do that in the middle of here. So I can say vec3, I'm going to call it normal color, is going to be texture 2D. We're going to sample from sampler normal map. Our UV coordinate is just going to be v underscore UV, the same as our diffuse texture color, our starting color as I've named it. Whenever you use additional texture maps when you're rendering stuff in 3D, the texture mapping, so the UV coordinates on all those textures will be exactly the same, so you don't need to pass in a separate set of texture UVs for the normal map and for the diffuse color texture or the specular color texture or the ambient color texture or anything like that. Just a general rule. They don't necessarily have to be the same size. You might sometimes find that in this case even, the size of the diffuse texture map is 512 squared, but the size of the normal map is 256 squared. That's fine, as long as it's got the same relative proportions are going to be okay. If you wanted to just, for example, render the normal map itself, you might do this just to see if everything's working okay. Let's make that a vector 4 of the normal color RGB and alpha of 1. If we want to make sure that we are indeed sampling from the normal map correctly. What don't you like about that? Oh, that needs to be .rgb because vectors 3s and vector 4s. Let's see. Oh yes, I'm not actually submitting this with a normal map. So how do I want to do this? So when I submit, for example, vb underscore ground, texture set stage. The stage can be shader get sampler index, shader basic 3D stuff. The name is samp underscore normal. And the texture ID is going to be sprite get texture, SPR ground normal, sprite frame 0. For the Master Sword and for the Master Sword sheath, we can... Oops. We can do the same thing. Yes, when you hover over one of these sprite names in Feather, it will preview it for you. Feather's nice when it works properly. I give it a lot of grief, but it's been working properly more and more often as it gets fixed a little bit more in every update. Anyway, we're now rendering the normal map, and this is alright, very pretty greens, blues, light greens, magentas. Magenta's a very harsh color on its own, but when you do combine it with something like the other colors you might find in a normal map, it's quite nice. Alright. So as I've said, the value that you sample off the normal map is going to be in tangent space for each fragment. And that means that a normal vector that's pointing straight out is going to have a, in tangent space, that's going to have a value of 0, 0, 1. So it's going to be 0 on the x and y and 1 on the z axis. This is why a lot of normal maps that you'll see are going to be this lightish blue color, because if you take that 0, 0, 1 vector and if you encode it as a color with channel values between 0 and 1, you're going to get 0.5, 0.51, and that is the color code of a nice light blue like this. If you have a vector from a normal map that is pointing a little bit off to one side or the other, it's going to have a value that might be something a little bit more like, let's say 1.0, 0.5, 0.5, and in that case, you're going to have a more magenta or a more light green color. Once again, if you encode those values as a color. So if you ever wondered why normal maps look the way they do, that's why. As I said, we're going to need to actually convert this from tangent space into world space, and we can do that by, shall I call it, what shall I call it? Vec3, I'll call it transformed normal. We can multiply the v underscore tbn matrix by the normal color. We're going to want to normalize this. It should already be normalized, but it never hurts. The components of the TBN matrix should all have magnitudes of 1. The value that you get from the normal map should have a value of 1. Speaking of which, I'm going to want to, and I mentioned this when it came to the colors in the vertex shader, I'm going to want to multiply this by 2.0 and subtract 1.0 to put that in the appropriate range. If you forget to do that, you'll get some weird lighting issues that might take you a minute to figure out why it's not working the way you think it will. And once we have this transformed normal, this is what we can replace the normal that we might have obtained from the vertex shader with. If you do any lighting calculations, any n.ls, anything like that, we can apparently continue encoding the normal as a color, which I don't want to do. Let's comment that out. We can run the game, and now we can see that the light is coming down in about this direction, and we've got what looks like a little bit more geometric detail on these models. For example, if I were to freeze frame about here, we can see what looks like a few additional ridges on, for example, the sheath of this Master Sword or on the handle of this Master Sword, but as it happens, reality is but an illusion. That is not real geometric detail, that is just a few tricks with a fancy normal map. And the light isn't moving, but if the light was moving around, we would be able to also see it on the ground. So let's actually... let's actually make a dynamic light, pass that in as a uniform, and let me just have a directional light that kind of rotates on the spot. All right, we can have a light that's set up something like this. This is just a light that's rotating on the spot. I've given it a slightly different rotational period than the sword and the sheath, so that it's not pointing in the same direction relative to them at all times, but it's going to be rotating. It's going to be pointing downwards at the ground. And if I were to just stay here, you can see that it looks like the and this is actually a little bit dizzying because of the exact like brick texture that I picked, but it looks like the sides of the bricks on the ground here are being lit from different angles depending on where the light is shining from. And then, of course, as before, there is the way the light is interacting with the sword and the sheath. All right, so that's fun. That's the basics of normal mapping. I do want to make another additional supplemental video on this at some point. Not sure when. It might be next week after this, next Saturday. It might be a little bit later than that, depending on when I have time. But I do want to talk about a few more things, particularly regarding how the TBN vectors are calculated. And if there's anything else that I think of, or anything else that someone mentions in the comment that I think is worth talking about later on, I'll do that as well. Otherwise, that's going to do it for me for today. If you want the code for this, look for the GitHub repository down in the video description. One of these days, I will probably update my 3D lighting related extensions to support normal mapping, because I've been slacking on that for like 2 years. I'll have links to all that stuff down in the video description. I try to post about 2 game dev videos a week, one tutorial like this, and one Let's Make a Game, currently a 3D Zelda-like wizard game, so if any of that appeals to you, feel free to subscribe. I have a Patreon, so if you want to contribute to the channel, links to that can be found in all the usual places. Otherwise, I hope you all found this interesting, and I will see you all later. By the way, one last bit, and I don't know honestly where I would stick this if I didn't mention it here, but you can totally get away with just using a color attribute for any old normal vector. You don't have to just use it for the TBN. The advantage of doing that is that while you would have to do a little bit of silly decoding a normal vector as a color like this for just like the regular vertex normal, it would take up slightly less space. So a vector 3 attribute for normal takes up 12 bytes per vertex, but a color attribute only takes up 4. And if you don't need that degree of precision for your normal vectors, you can totally just encode all your normals as a color and save 8 bytes per vertex. Special thanks to DJ Gibbles, Edward Holt, GameMaker, Manta Ray, Sindra Larson, Squarecrow, VitroV, and Zenjamin for supporting these videos. If you want to contribute to the channel, head on over to the Patreon page down in the video description to join the fun.